Alright, hello ladies and gentlemen, welcome to a lecture series on Structural Analysis 1. Today we're doing a review of statics, and I think it's important to start off by thinking about what statics really means. Statics is the study of the flow of forces and the corresponding internal and external displacements of structural systems at a slow speed. And that's really the important distinction that we need to make between statics and the concept of dynamics. Dynamics is the same thing, but for forces being applied at higher rates. And I'll hopefully post another lecture series on structural dynamics, and after that, some on more advanced experimental dynamics. So today we're doing a review of statics. And statics really begins with Newton's third law, which states that for every action there's an equal and opposite reaction. And it really has to do with the concept of equilibrium. Now, what is equilibrium? Equilibrium looks at any physical object. You can have any arbitrarily shaped object. I'm going to draw this random looking shape, and it looks at all the physical forces that are applied to this object, and it states that for every action there's an equal and opposite reaction. So the action of any of these forces must be cancelled in some physical way by the other reaction forces and the other external forces that are being applied on this physical object. And by the way, this kind of diagram in structural engineering is typically referred to as a free body diagram, FBD. FBDs are really important for analysis, and we'll use them quite often. And so what equilibrium really tells us is that the sum of forces in the x direction equal to 0, and the sum of forces in the y direction equal to 0. We're not going to look at the z-axis because here we're only looking at the two-dimensional objects. And lastly, around any central point on this physical object, the sum of moments equal to 0. And in fact, I can draw moments on this physical item as well. So these moments have to cancel each other out, and also they have to cancel out the resultant moments that's getting created by these forces getting applied on this physical item. So that's really an important concept that we need to think about. Now, anytime we're trying to solve the behavior of some physical item, like the one we're seeing in front of us, we have to think about two very important concepts. These concepts are called, the first one is called determinacy. So and the second of which is called stability. Stability, as you may have experienced in your personal lives, is very intuitive. Anytime you don't have equilibrium, for instance, you have stability issues. So your a physical object goes from a state of being at rest to a state of motion and perhaps acceleration because the resultant forces are not equal to 0. But to begin with, we're going to focus on determinacy and what it means for a structural system to be determinate. there is a very basic definition that states that when the unknown forces inside a structure, so if you're looking at a truss system, when the forces within each truss element can be determined statically from simply the equilibrium equations, and the equilibrium equations are pretty much these forces shown here, these equations shown here. Oops. We're going to refer to these as the equilibrium equations. Then the structure is statically determinate. So if these equations are sufficient for solving and identifying all the internal forces inside a structure, then that structure is statically determinate. However, if those equations are not sufficient, we typically have to refer to other equations, and those equations are called compatibility equations. And compatibility equations are based off of the material properties and some of the geometric properties of physical systems. So we utilize those properties to obtain additional equations, and having more equations per unknown, per the number of unknowns, allow us to solve more unknowns. And so that's really what the concept of determinacy means. So I'd like to highlight the equilibrium equations here. So equilibrium equations alone are sufficient for a determinate structure, and compatibility equations are necessary for indeterminate structures. In this course, we're going to start off by looking at determinate structures, which is something I'm assuming you're fairly comfortable with because those are taught in more high school level courses or first or second year of college courses. And then indeterminate structures are typically taught on more advanced structural analysis type courses. And this is one of those courses. We're going to get into those, and we're going to show you different methods for solving the internal forces and displacements within structures. And so let us look at the concept of stability now. For stability, we have to separate beams and trusses and look at them separately, really. We're going to start off by looking at beams. With beams, we're going to say we're going to limit things to a 2D, two-dimensional coplanar structure. So whatever we see on the face of this page, three-dimensional beings make things more sophisticated, and we'll leave that up to you to figure out the equations for and to analyze. So we're going to say for a coplanar beam structure, we introduce a variable called n, which is for the number of elements or parts. And we're going to introduce a variable r, which is for the number of reactions. Anytime r is equal to 3n, so this is 3 times n, we can say that the structure is determinate. And anytime r is greater than 3, and we can say that our structure is, in fact, indeterminate. So under such circumstances where we have indeterminacy, we're going to need to look at the physical or material properties of the structure, and to formulate compatibility equations and be able to solve indeterminate structures. And clearly, when there are less reactions than 3 times the number of elements, we can say we have stability issues. Stability is very complicated, so here I'm just going to explain it as stability issues and not just instability, because there are circumstances under which this condition can be satisfied and you may still have stability. So let us look at a simple arch. A simple arch bridge you may have seen around, perhaps in your cities, in your towns. And we're going to introduce this arch here. That's going to have this central hinge. And we're going to have pinned connections at the 2 ends of our arch. And if we were to draw the free body diagram for this arch by separating out the structure at the location of all the hinges, we would have these vertical and horizontal forces, these ones. The counterparts to those would be in the opposite direction, and these reaction forces. So if we're looking at this structure, this arch structure with the hinge in the middle, we're going to have 6 reactions in total, as shown in this free body diagram. This is an FBD. So R is equal to 6, and N is in fact equal to 2. We're looking at 2 elements. We have divided the structure at the location of the hinges. And so we can say that R is in fact equal to 3 times N, thereby this structure is determinate. So with this structure, we don't need to know what the material properties are or what the geometric conditions are. We can simply solve by looking at some of the dimensions and how the external forces are being applied. Now, let's make this a little more sophisticated. What if I gave you the same structure, but this time we don't have the middle hinge. This time we simply have my pin supports at the very end, and I really don't have any more hinges in the middle. Then I can say that I have 4 reactions, 2 at each support, and I have a symbol or a single element describing the entirety of my structure. So here I can say that R is in fact greater than 3n, because 3 times n is equal to 3, and so we have an indeterminate. We have an indeterminate structure. Okay, so that's really one way to look at determinacy and how determinacy ties into instability. There are other ways instability can occur, and we're gonna look at some examples of them. Those are really rare, and but they are small details that you should pay attention to as engineers. Suppose I have some sort of beam that looks like this, and so here we're looking at instability. And we have slanted reactions on this beam. And there is one in the middle. If I were to apply some physical load with a value of P, I would have reactions, which I'm going to draw in different colors, that would look like that, and perhaps like that. And so if I retraced all these reactions back to some central point and looked at where they coincided, and if they all sort of coincide at a single point, then that becomes problematic, because basically I can have instability issues. Something I have to fix with this drawing is my reaction at this corner. This should have been a roller, not a pinned connection. So a roller looks slightly different. It has these this type of support, little circles underneath it. So nothing is pretty much fixed here. We have vertical supports, and their corresponding reaction forces are going to a single central point. We're just going to refer to it by C. And so any tiny lateral force will make this entire structure rotate about C. So this is an instability problem, and even though we have full determinacy, we have a lot of reactions for the given structure that we have, we're still going to face instability. So this is one type of instability, and it's typically described via support reactions being concurrent at a single point. I'm going to write that down. At a point. We are. There could be other examples where we have rigid body motion, and rigid body motion is a much more common problem, and typically it manifests itself whenever we have some tiny failure where one element within the structure fails, and we end up getting disastrous rigid body motions where the structure as a whole moves. So suppose I have an L-shaped structure. I should probably pay a little more attention to this detail here and this detail here. And we have a roller and a rocker type connection here, and these reactions are providing support in the vertical and moment. But if I were to apply a force in the lateral direction with a magnitude of P, I can easily see that my structure will accelerate, because there is nothing really resisting this lateral force, this horizontal force, and the supports. None of these supports can resist horizontal reaction. So this is another type of failure, and we call this reactive forces are parallel. This is another kind of instability problem. And so we've talked about instability and how it manifests itself within beam structures. This can also happen within truss structures. So we're going to look at the determinacy and the stability of truss structures. So anytime we're looking at coplanar truss structures, We are going to define several new variables. These are B for number of bars, R for number of reactions, and at last J for number of joints. We're going to define three formulations. These are B plus R is equal to 2J. We have determinacy. So our structure, our truss structure, will be determinate. If B plus R is greater than 2J, we're going to have indeterminacy. And when B plus R is less than 2J, we tend to have instability. So our structure is going to be unstable, perhaps globally, perhaps locally at a single element. And so let's look at an example. Since it's difficult to draw straight lines, given this physical system that I have here in front of me, I'm gonna, perhaps I should write down, just to keep things organized, we're gonna say, we're doing an example. I personally love examples because examples are really how you get to learn and test your skills and your understanding of concepts. So I have this truss-like structure that looks like that. These lines help me recreate truss-like structures and makes things quite easier. And so this is a truss structure, and it has braces in the middle, and the braces are separated to indicate that in fact they are not touching. So we have some sort of slider support here. This is a slider. It has the circles underneath it. We have a roller support here, and the roller support, or excuse me, a pin support here and a pin support here. So anytime you see those little circles, little hollow or black circles underneath my connections, you can think of those as a slider. And these two on the top right corner and the bottom left corner are pin supports. So with this kind of reaction, we have, if we're looking at the number of bars, we have B is equal to 5. So 1, 2, 3, 4, 5, 6. So excuse me, in fact this should be 6. And if we're looking at the number of supports, we have 2 at the pins, so 2 plus 2, and at the slider we have 1. You may be asking, why don't we have the moment? Because we're only looking at truss structures, and moments don't really exist in truss structures. So R is going to be equal to 5, and J will look at the number of hinges. So that's 1, 2, 3, and 4 at the 4 corners. So J is equal to 4. So if I'm looking at these relationships up here, we have B plus R is greater than 2J. So 11 is in fact greater than 8. And so we have a degree of, this is a D, degree of in determinacy, I like to refer to it as DOI of 11 minus 8 is equal to 3. That's what we have. Okay, so lastly, I'd like to look at an example where we're gonna solve a truss-like structure and keep things organized. We're gonna write down example, and again, I'm gonna use these linear sections to describe my physical system. So we have this kind of truss, and has diagonal braces and another diagonal brace here. Perfect. And so I have a joint here, a joint here, one here, here, and here. And there is no joint at the section of these two braces in the middle. And I have pin support at this end, and I have another one over here. And there are two forces that are being applied of magnitude 8 kilonewtons, and one here at a magnitude of 8 kilonewtons as well. In these lecture series, I'm going to look at the metric system, so we're going to be looking at things in terms of newtons and meters and millimeters, and also we're going to look at the imperial system because a lot of our viewers are going to be studying and living in America, and things are looked at in inches and feet and perhaps kips, which means kilopounds. So if I were to solve a structure that looks like this, I first have to identify what the dimensions are. I'm going to say we have 3 meters here in this bay, another 3 meters here, and 3 meters between these two roller supports. And so I'd like to identify each of my joints now. I have A, B, C, D, and E. Makes things a little easier when we're trying to identify which joints we're analyzing, and really we're gonna just start things by looking at joint C. This is a statically determinate structure. We're not still at a phase in our understanding of looking at indeterminate structures, so we're going to limit this example and this analysis to statically determinate structures. So we're looking at joint C, and joint C has this vertical force of 8 kilonewtons being applied, and these supports, these internal forces, FCB and FCD, that we have to really look at. So if I'm looking at this free body diagram, this FBD here, and I'm solving for sigma Fy, I simply want to solve for the vertical forces and make sure they equal to 0. I can say that minus 8, it's minus 8 because down and left are negative. Minus FCD sine 45. The angle for element CD is 45 degrees because it has horizontal and vertical dimensions of 3 meters. It makes it a 45-degree angle. Is equal to 0. And so if I simply pulled my calculator and solved for FCD, I would have a value of 11.3 kilonewtons. Now, we're probably wondering, is this element in compression or is it in tension? And so it's really straightforward to look at. FCD is countering the vertical force of 8 kilonewtons, and its value has a magnitude of minus 11.3 per this equation. So if I'm pointed this way, per how I've described it here, how I've described FCD here, I have a magnitude of minus 11.3. So I can make this vector, this force vector, 11.3. And so if I have a node and I have 11.3 being applied on it, it means that my member is in compression. So if a member is in compression, it's applying forces towards the hinges, towards the joints. So FCD is equal to 11.3 kilonewtons compression. I like to put a C inside two brackets. So I don't really like the concept of minus or plus when I'm looking at the internal forces in a truss. I like to know if they're in compression or tension, and they are in compression in this instance. And so once I know what FCD is, then I can pretty much figure out what FCB is by saying, sigma fx is equal to 0, and I have 11.3 cosine 45 minus FCB is equal to 0. And so I have an FCB value of 8 kilonewtons. Okay? Alright, so we have two of these elements solved. We have to look at 1, 2, 3, 4. We have 4 more elements to solve. Now we're going to look at joint D. So we have joint D, and there is a force of 11.3 being applied here. This was one of the forces we obtained earlier. And there is a force of FDA, that's an unknown one. This is something we're going to look at. And the horizontal one of FED that we're going to look at. And so, again, we're going to do sigma Fy is equal to 0, sigma standing for the sum of, and we have minus 11.3 sine of 45 plus FDA sine of 45 equaling 0. This is only in the vertical direction. FED plays no part in the vertical direction, and we can simply ignore it. And so FDA is going to give us a value of 11.3 kilonewtons. This time the joint is getting pulled, getting dragged, and so the element must be in tension. That's how I like to think about my elements. If they are pushing on the joint, I have compression, and if they're pulling on the joint, I have tension. And so the sum of the forces in the x direction will simply equal to, let's see, we have minus 11.3 cosine 45, and we have minus 11.3 cosine 45, so we have two of these, and we have FDE, and this thing equals to 0. And thereby, FDE is going to equal 16 kilonewtons. It's pushing on the joint, so we have compression. That's what it is. Lastly, we're going to look at joint B. And with B, we have a little more, we have a couple more forces than we're used to. We have this 8 kilonewton, which was solved earlier. We have the externally applied load of 8 kilonewtons. This FBE here, and this last unknown, which is FBA. And so if we do sigma Fy around joint B, we're gonna get FBE sine 45 minus 8 is equal to 0. FB is going to have a value of 11.3 kilonewtons. That's the magnitude, and it's in compression. And we're going to do sigma Fx is equal to 0. And this will give us 8 plus 11.3. And this equals to 0. And thereby, FBA will have a magnitude of 24 kilonewtons, and it will be in tension. So element BA is pretty much the element that will take the greatest amount of tension and greatest amount of force inside this truss structure. So having said that, we've solved this truss structure. Today we've looked at determinacy of stability, determinacy and stability of beams and truss structures, and we have looked at statically determinate truss structure. This has been a review. Hopefully it has been a comprehensive enough review for most of you. If there are any questions, leave them in the comment section. I'll try to answer them to the best of my ability. And in the next lecture, we're going to look at shear force and bending moment diagrams, and that's also going to be a review of beams. And we're going to do a couple examples together, and hopefully we'll dive right into more advanced examples right after that particular lecture. So I'll see you in the next lecture. Have a great day.